Hey everyone, welcome to our weekly EAT. So thanks everyone for joining. We're going to go ahead and get started. Today we have our ConOps and it's going to be presented by Kate. And so I'm going to let her just take it away.
Hi everyone. Feel free to stop me throughout this briefing if you have any questions, but my name is Kate. I am a proud UNP alumna. I participated in NS8. And then when I graduated, I joined the UNP program office for a couple of years as a systems engineer, and now work for the small satellite portfolio at AFRL, managing one of our in-house programs. I will caveat that this is an expert area telecon, but I don't think technically I qualify as an expert on ConOps and experiment planning. I think there's a specific hour requirement for that. I have some experience in it and I've seen a lot of them. So I'm going to talk through these two topics today. And the goal of this presentation is not to give you a template to do both of these or either of these documents with, but is rather to give you some context on how these fit together, how they fit into your overall plan and mission development process, and then kind of give you the key elements of what we look for in an experiment plan or ConOps, and to give you guys some context on how it's useful to you. So we'll start in kind of with some front matter. Why do these two things matter? I, as a UNP student, and even later too, sometimes struggle with documenting for document's sake, I have to fill out a ConOps, I have to fill out an experiment plan. But really I hope you view these two documents as a potentially useful tool to you. Seeing this systems engineering V in the last couple of EATs, I believe. And so as you're kind of going through this process, it looks really simple, or maybe not so simple in this diagram, but when you're going through it, there's a lot of kind of connective tissue between each step in the V, and then as you can see across as well. And so the experiment plan and the ConOps can really enable you to get through this in a clean way and document it well, but really as a tool of understanding can give you a plan. So your operators will thank you at the end, your stakeholders will be happy, and you can communicate well throughout. That's how I have used these documents in the past, and I think the major benefit they give. So we'll hop to the next slide here. Definitions. So a little bit of a disclaimer, these are definitions that came out of my brain and not a specific source. So take that with a grain of salt. But I think in line with what your user's guide says and kind of the UNP doctrine, if you will, there's different purposes for each of these components that all kind of are codified as mission definition or mission design. And so we're going to talk about them separately today, but I want to make it very clear that these are all very interrelated and important together and important distinctly. So for the sake of this presentation, we're not talking about mission objectives. Hopefully you all have started to get a handle on those for your own programs, but mission objectives and design documents, that describes the need, the goals of the program, and why you're doing it. So that would kind of codify your mission objectives, success criteria, defining stakeholders, and defining the scope of the mission. The experiment plan is kind of a continuation of that. And instead of the why, it starts to target the what. So you start to describe goals, targets, test parameters, and frameworks, and really the key parameters and key meaningful data that tells you that you've done the experiment well. So if we think about the scientific process, right, you've got your problem statement and your hypothesis, and at the end of the day, everything you do is to prove those things out, right? And so that's what our experiment plan does. It tells us what we're doing to fulfill our why. And then kind of overlapping that is the concept of operation. So ConOps stands for concept of operations. You will see that term used in your career to address all different kinds of things, but in the world of small satellite, ConOps describes the how to do the satellite. So it describes how the experiment can be achieved. It describes things like software behavior needs, how you handle faults, and it will ultimately describe kind of your pass-to-pass procedures at a high level that you'll need to do in order to achieve your mission. Really quickly on this slide, this is not new information, but fundamentally what we're talking about today is these two pieces, and they have a lot of overlap. And so one of the things I hope you take away from this is a little bit of deeper understanding on what we're trying to ask of you so that you can achieve these things, but further some flexibility on how you communicate. So the experiment plan and the ConOps are distinct things with distinct purpose, but the overlap is ultimately in your experiment design. And so you'll see a lot of crossover in your documentation, and how you handle that is completely up to you and your team. The key thing is that you truly understand what you're trying to achieve versus how perfect is my document, right? Really quick, but before we start getting into each of these elements, I just want to make a note here as well. I think you've seen this flowchart in a number of presentations prior, and ultimately the ConOps and the experiment plan are both tools to help you kind of hone in on this process. And so there's a chicken and the egg, right? Ultimately, what comes first, the ConOps or your system budgets or the experiment plan or the system design? It depends. I like starting with the ConOps and experiment plan, but of course you need to have a little bit of kind of assumption about what that system looks like before you can get there. So it's an iterative process that you're going to go through, and you can treat that process as an opportunity to kind of suss out what's important that helps you define your requirements and better communicate with all stakeholders involved, whether that be your PI or the UNP program office or others, right? These are tools to help you understand that, to iterate better. So before we jump into the experiment plan, I did want to talk through an example mission set. So I'm going to use this example throughout the presentation, but we'll use this kind of high-level mission set to break down what an experiment plan could look like and what a ConOps could look like. Our experiment mission statement is count vehicles in specific areas from a space-based platform to determine consumer traffic trends in order to assess parking needs and traffic flow. We could talk literally all day about how good or not good these statement objectives and success criteria are. For the sake of this, we're just going to take these at face value and make some assumptions about what the stakeholders meant. So for our objectives, we want to identify vehicles within an image with 90% accuracy. We want to image the same location at least once daily, and we want to geolocate images to within 50 meters. So ultimately, our objectives support the idea that we want to understand traffic trends. The mission success criteria that we've defined for ourselves is we obtain car quantity for a single location at the same time daily for 7 days. And then on full success, we up the ante for 5 locations at the same time daily for 49 days. So this is the basic premise. I think we can kind of all basically wrap our heads around it. You got an imager in space that's flying over a city and making sure that we can track the flow through a visual image of the same spot. So now that we got that out of the way, we'll jump into the experiment plan. So backing up a bit, again, the experiment plan is what are we doing and what do we need to do to make it meaningful? And so we have these mission statement and objectives and success criteria defined, and we have a basic idea of what our mission should do. But if you start to think about requirements derivation, or even like how I would design it, there's still pieces you're missing, right? So there's a lot of assumptions you can make, but ultimately you want to have a very clear understanding of what is actually trying to be done. So in some ways, this experiment plan becomes kind of a negotiation between the team executing and the stakeholders or the PI. I will say, just for some background context, the experiment plan is not something that at least I've seen in any NASA documents or like SMAD, for example. ConOps is a fairly well understood concept industry-wide. The experiment plan actually came out of AFRL. So this is kind of an AFRL document that we make our own missions do as an R&D organization to help us kind of define these interim pieces and make sure all parties are aware of what's going on. So this is probably more akin to something in NASA, like a science plan or something like that. And I hope you'll be able to see very shortly here that there's high value in it, even if we made it up for ourselves. So some of the key questions: what locations matter? So if you look at, there's the mission statement, objectives, and success criteria, but we don't know enough yet, right? So some key questions that maybe the experiment plan starts to broach on are: what locations matter? What are locational priorities? How do we post-process data products to get that 90% accuracy? What time cadence matters? So we know it's daily, but does it matter what time of day? Does it matter if we were to do more than one location, kind of how close in time those are to each other relatively? What resolution is meaningful? So we have an accuracy, but what kind of resolution do we need? Can I capture multiple locations? What are the key performance indicators or parameters of the experiment? So it's a little bit of a buzzword, but there's kind of a question of how much data is meaningful. And then how many passes will the experiment take? So for mission success criteria 1, is it I only need 7 images and I'm good to go? Or are there things that we're missing there once we play that experiment out? So on the next slide, I've kind of broken out the basic experiment plan elements that we look for, right? So if you look on the left-hand side, you've got your experiment definition, your experiment priority, and your experiment parameters. And these are kind of categories that I made up based on seeing a few of these. And so the idea here is that experiment definition, you got to define what you're doing. So that one's pretty straightforward. But then once you start to look at it, maybe you only have one experiment and that's good for you and that's perfect. But there's priorities within that experiment. Maybe you have multiple experiments. And even in that case, you still need to define priority, right? So you understand what you're doing, you know what priority they're in, and then you need to identify the parameters for every experiment you do. An example for experiment priority, we look over on kind of the top hand side. There's a lot of ways you can slice and dice this, having kind of briefly heard some of the high level overviews of all of the NS11 missions. A lot of you are going to approach this in very different ways. And these are just 3 ways, and they're not all of the ways. There's lots of ways to do this, but sometimes you have a singular payload that you have kind of staged experiments for. Sometimes you have priorities in those experiments. Sometimes you don't. Sometimes you have multiple payloads and you do them one at a time, and then you test them all together. And sometimes you just have one shot experiment, right? So example of that is something separating from the launch vehicle and making an observation of it. That would be a one-shot experiment, and that works too. But the important piece here is that you define what that is and have a clear understanding so that you can move on to your experimental parameters and start to define what that is. So I've broken out some of the characteristics that we've used, and I use this kind of template from my own mission of what we defined in our experiment plan. And that'll include things like the specific experiment objectives, which should always point back to your mission objectives, but won't necessarily be the same. Entry or exit criteria or constraints for the experiment, experimental success. The data telemetry and products is probably the most important piece if you do nothing else. And identifying what specifically you need to get on the ground in order to achieve your experiment. Does that mean you just need images? Does that mean you need time-stamped images? Does that mean you need GPS data along with those images, right? So this is kind of a further codification of what defines success criteria, but even more abstracted from that as a user, what is meaningful for me to be able to say, hey, I either proved or disproved what I was trying to do. You also want to consider things like timing requirements. Do experiments happen at a specific time? What about relative timing between experiments? Those types of things. This might start to overlap a little bit with ConOps, but your configuration. So not just your spacecraft configuration, but your ground configuration, or maybe in our example case, what locations we're targeting, and then spacecraft configuration as well. And again, a lot of this starts to overlap with the ConOps, and that's okay. Defining these things well is the goal, again, of both of these documents. So moving on into our next slide here, we'll start to break down our example. So again, mission statement, objective, success criteria. There's clues in each of these items, a few of which I've called out, that'll kind of start to guide us to how do we design our various experiments. The first kind of call out I have here, there's a part of the mission objective that's very specific about geolocating images to within 50 meters. This leads to kind of a question regarding data integrity and data processing, and that's a key thing to kind of hone in on the experiment design. Better understanding that as a requirement, and then better understanding how you would facilitate that within your operations campaign kind of all coalesces into this experiment plan. If you look at the success criteria, this is where we start to really break down our design element. The first success criteria suggests that there's probably a priority location. And so figuring out what that is and why that is the way it is an important part of the stakeholder engagement that is involved in this process. There's a statement here that is, this could be a single experiment on its own. And we can guess that 7 days is probably significant. It's probably because it's a week, right? You could say, I just want to do one experiment to meet my mission success criteria before I do anything else. And when I say you could do that, the light suggestion is you probably should. And that is mission success, right? And so that's an important thing to kind of hone in on. The third thing I noticed here is we're expanding to 5 locations and for a longer duration. But there's a question of, do these 5 locations, are they fairly co-located? Are they separated by a lot? And so when you start to think about your mission design as an experiment, you start to say, okay, is that something that I can do in a single pass, or do I need 5 passes in a day every day? And the answer to that is going to be very stakeholder dependent, but it's something that you start to, again, suss out in this process. And finally, the call out that looks like it's going to nothing. Part of the other benefit of an experiment plan is that you can start to define where lines are or boundaries are. And we'll talk about this more in depth in a later slide, but you will always have stakeholders, including this office, that will ask you, well, if full success is only 49 days, what happens at day 50? And I hate that question as a mission manager, but I ask it as a reviewer. So it is something that you have to think about. That's part of this process. But as an experiment plan, you can say, oh, okay, look, there's the full success category and there's a stretch success category. And maybe there isn't for you, and that's okay too. But in the case that it is, if you could have ongoing experiments, you can say, look, in my experiment plan, I'm kind of outlining what these first set of experiments look like. And then later on, I can decide based on available resources what to do. So that's just a little bit of constraint-based engineering plug, but it's something to consider when you're writing these documents. Moral of the story, a lot of these questions can get asked, and that ultimately is an opportunity to clarify your objectives and what you're trying to do with stakeholders. So I took a stab at this, and it's not perfect. Honestly, I don't know if it's even any good, but you can start to break out experiments, right, from these statements. So like I mentioned, we're going to do experiment A, single site, meet minimum success criteria. Well, what about another site that's nearby or maybe not nearby, but we want to do the same thing? Well, you could codify that as just another experiment A. You could call it experiment B, however you want to organize it, that works. I've called that experiment C. So now we're talking about our full success. Using the same aperture, we're going to make the assumption on this example that you want to collect 5 sites in a single pass. So maybe we have a wide enough kind of ground footprint in our aperture to collect 5 sites in a single pass that's meaningful to the stakeholder. If that's the case, then experiment C is our full success. Then we can also say, well, maybe because we have this asset available to us on orbit, we can expand that to multiple non-co-located sites. That would be an experiment on its own, potentially. You could do that in a temporal sense too. So maybe later on in the mission, I'm up there for 6 months and I say, well, now it's Christmas time and I want to know what experiment B or A is like, but at a different time of year, because maybe that matters to my stakeholder. All of these kind of drafts of experiments, you would then take back to your stakeholder and say, look, is this what you're looking for? Is this meaningful to you? We're going to assume it is by no basis, but we're going to assume that these experiment drafts are a good stab. And there are a lot of ways you could break this out. You could do experiments based on site locations. It doesn't have to be as codified as this. It depends on what your stakeholder is ultimately looking for. But at the end of the day, this is a communication tool for you to kind of break out things and design things following this. If we break that out a little further or clarify this more and start to look at priority, you can note a couple things. So first, we've hinted at this several times, but experiment A means if I do experiment A, I have a successful mission. It's minimum mission success. Then if you look at experiment C, I think as long as the stakeholder is cool with it, I meet full success with experiment C. Awesome. I might want to do those 2 things first. Before we get into priority too much further, I do want to say this as well, kind of in family with the constraint based. You also want to kind of draw a line and say, look, if I get experiment C done, I'm good. And that to me is called the design line. So you can always try to shoot for experiment D and E, but that should never be at the sake of completing experiments A through C in this example. Always want to design to full success. And then beyond that, plan and accommodate as your resources are available to you. And so that means if experiment E is outside of my full success, I'm not going to dedicate all my resources to achieving it. And in this mission, it doesn't matter nearly as much, but in some of yours, you might just start to see that gradation form and be able to draw a line more clearly as you start to distill requirements. Given all of those pieces, we can then start to establish priority and how we're going to do these from a temporal sense. And then, like I said, in a resource dedication sense. I kind of diagram this like on the former slide that shows, look, obviously we want to do experiment A first. In some senses, it's a pretty easy thing to do. And if we can't do that, we fail. So very easy, obvious experiment A. Then you might want to look at the choice. Experiment B is a lot easier to do. So maybe I can do that before I do experiment C, maybe not. It depends on what the stakeholder wants. It depends on what your team is capable of doing, all those pieces. You can kind of establish experiments D, E, and E later. This is a little bit pedantic, but the point here is that you want to start understanding these things so that you can communicate them outward. And this is a way to facilitate that. Then when I start to think about prioritizing experiments A and C, or maybe even B, I think about, okay, how do I actually achieve that on orbit? And so you want to make considerations like, how many passes in a day do I get? Do my passes need to be co-located with my ground terminal? Do I need that data in a fast manner between experiments? Can I power my payload in those consecutive passes? What maneuvering do I need? How do I know where I'm pointing, and all those pieces? One of the things that's listed here on this chart is this elevation map. You can kind of just see, this is an excerpt from, again, the mission I am on. Our experiment plan says, look, I need access times at a specific location. So we mapped out, okay, use STK, and for the orbit we think we're going to do, how often am I going to be able to see that ground site? And that very quickly both led to orbital requirements, but also led to an idea of what our experimental cadence can be. And if that wasn't good enough, we could start to think about ways how to improve that, right? So this is a very early analysis that you can do to help kind of establish the feasibility of a given set of experiments. Moving to the next chart. So I just broke out some of the experimental parameters based on kind of the initial chart that I showed. And we don't have a ton of time to talk through each of these in a lot of detail, but basically the idea is when you start to break this out, you're going to either want to, in a document, create a small table for each experiment, or at least define it somehow. And so when you look at our example, the objective, what are we trying to do? Well, it's pretty straightforward. As we noted in the success criteria, there were questions that wouldn't get us directly to a requirement. And so this is your opportunity to kind of better codify that. We're trying to post-process data for a single location image daily once a week. And note the verbiage there, that's very specific. Not just are we collecting data, but we also have to post-process it and count vehicles, right? And so that means that we're downlinking that data. That means that someone is sitting at a terminal, or you've got a piece of software that is making all of the right data products out of your image. And so at this point, you can kind of start to see some design trades that manifest. Maybe you're trading resolution versus field of view and different things like that. But this is starting to kind of hint at those design criteria. You also want to consider things like your entry or constraints. In this case, experiment A, you had to have completed camera checkout and ADCS checkout to do this successfully. And you also have to have fairly consistent access times in a stable vehicle. When you get down to experiment C, not only do you need all the same things, but you also need to have done experiment A, right? So that you start to understand kind of the order of operations and truly informing your ConOps when you start to define things this way. Again, we're talking about what kind of data product do I need, just an image, time-stamped image, etc. The data products associated with that, like I just mentioned, are important here as well. Timing requirements and then various configurations are key components that you will need to define. The final note on this slide, sometimes these experiments are very similar, and that's okay. Again, this is a communication tool for you to both understand the similarities and differences and how that impacts your design and your ConOps. Last thing on the experiment plan, why does this even matter? Well, we've kind of talked about this throughout, but this informs things like orbital requirements, payload selection, overall hardware selection, your system budgets, all those things. But really, you're starting to overlay that with the ConOps. And we'll talk about that next. But having a clear idea of what you're trying to do in the experiment plan makes the ConOps a lot easier. And so you're going to have a feedback loop between those pieces. But this is a good place to start because this is what your stakeholders are ultimately going to care about. ConOps. Like our experiment plan, there's elements to this document. We've broken those out into mission design, mission timeline, and vehicle state. And unlike experiment plan, the document we made up, ConOps is kind of a universally understood document. After this, if you want to look at SMAD, that's a good resource to kind of wrap your head around it in a different way. If you Googled it, there's things that would pop up, but this is kind of what we look for in a ConOps document for a CubeSat. So mission design includes all things controlling your satellite, right? So tasking, scheduling, and control, system level budget considerations, and then ultimately it drives your integrated system design and communications architecture. Your mission timeline is also a key component. Often this is what people just call the ConOps is your mission timeline, but there's a lot more to it than that. But this is an important element. So identifying success points, when do I achieve success, prioritization of objectives and actions, and then describe the flow and decision points across the mission. Vehicle state transitions and fault handling is also a key element here. Defining modes, and we'll talk about what that means, but defining modes for the vehicle, defining fault handling for the vehicle, and defining operator and vehicle touch points throughout the mission life. We'll go into each of these in more detail. Before we jump too far, I just want to make a quick note here. There's not a particularly good common vernacular across CubeSat ConOps. People say things that mean different things for the same word. The important thing, however you define it, is that you understand what you're talking about. In this case, for this presentation, we'll talk about an experiment, which we've already beat too much, but we talked about an experiment, which is a specifically defined goal-oriented test, collection, or demonstration. A mode, and contrarily, is a software configuration. So the state of the vehicle to achieve different behaviors. And then a phase in this presentation, again, is just a period of time where predefined activities exist. So a good example of a phase would be what we call LEOPS. A lot of people call LEOPS the first part of your mission or launching a LEOPS. So that's an example of a phase in this particular brief. Jumping into our first element, mission design. So this is the area where you're starting to think about what is my experimental cadence? What are the key vehicle functions? How do all my system budgets work? So how much power will I need in an experiment? How much will I need in a non-experiment? How much downlink time do I need? How much overall time do I need to get data down? Those types of things. That kind of falls into how many ground passes do I need in a day? If I don't have enough, how many ground stations do I need? It starts to also inform what operations tools look like. So again, we're using this document as a means to start adding meat to the bones of what our requirement set should look like. If we're talking about just the mission design element, which again is a facet of our ConOps, we start to look at the overall flow of an experiment. So we defined experiment A in our experiment plan, and we'll start to break down the functional blocks of what our satellite needs to do to achieve experiment A. We choose an image target. That's something our stakeholder told us. We want to image this specific geographic location. Then we need to determine when our satellite will fly over that. We'll need to schedule a collect on the spacecraft or image it. And then we'll need to configure the spacecraft for the clock. So make sure it's in the right attitude, it's pointing at the right thing. We'll actually take the image, and then we need to store the image, and then we need to downlink the image. And then someone on console will need to do data analysis. So each of these pieces is, we've got 8 pieces here, right? So the flow is long, even for a simple experiment. And each one of these pieces is really complicated. This is going to vary for every experiment you do and every mission you do. And so you need to spend enough or ample time thinking about what that looks like for each individual experiment. Further, for each image, we start to think about things like the data collect and the data downlink. Those are kind of the 2 broad categories of questions. And so I'm not going to read through all of these, but again, you start to consider the mechanics of the actual process you're putting your spacecraft through. You start to answer some of the questions in the experiment plan and vice versa. And so this is where we start to see that experimental design overlap, which is good, but is something to consider when you're documenting, of making sure that you're looking at both of these at the same time and accounting for all of these or whatever applicable questions you have on your mission set. A different way to view this, right? Similar behavior. This kind of breaks down the process in another way. The point of this slide is just to show you another way to capture that. If you kind of break down that diagram we talked about before, the data collect is the most complicated part. So here's kind of another way to process this. Visually, if you're going to add automation on your vehicle, that's something to consider as well. And so you'll start to see some of the decision points within this flow chart that guide you through, okay, how do I gracefully fall out of that? And we'll talk about faults in a minute. And this part gets complicated and is something that we want to see you thinking about as you start to draft your mission design. Okay, back to our elements. The other piece is timeline. That is probably best understood across people. So this is the way we like to visualize, at least on our in-house team, our ConOps flow. And we've found this particular framework to be very helpful in communicating. This statement is not that you need to replicate this for you, but you want to think thoroughly about how do you communicate where you are in a mission from a status standpoint, and how do you as an operator or designer know what you need to do to get through the mission set on a time-based domain. In our case, there's usually a bus commissioning phase, a payload commissioning phase, an experimentation phase, and then, like I said, we talk about stretch goals. The checkpoint here is kind of an artifact of how we do operations, but it's something to think about for you. Point is, this is kind of a convenient way to visualize how you walk through a ConOp. And it's helpful to kind of also demonstrate, okay, at this point I meet success criteria, at this point I meet full success, right? So start to think through it that way is helpful. We've also seen it this way a lot, kind of mapping out your ConOps in a time domain. I'm not going to lie, I kind of hate this chart, but it's a way to do it. It's not a terrible way to do it either, but you want to be careful that this is not the only ConOps you show us. Be careful when you talk about time domain. I think it's great to predict and guess because people are going to ask you, but you got to remember that your phase transitions are not usually actually time-based. They're goal-based or completion-based. And so just consider that when you're designing your ConOps. Final element we'll talk about today is vehicle state. I'm going to show a slide in a second that shows a mode transition diagram. But I want to be very clear that we are not saying you have to do modes this way. The goal in defining this in your ConOps is that you have a way to articulate to your team what your vehicle has to do in various activities in the program. And so a mode is typically a software configuration, like I said, that defines what is on at a given time, what you're doing, or what the default kind of attitude state is, default power state, like I mentioned, and then kind of the radio ConOps at a given period as well. This is a mode transition diagram we've used. Again, we're not saying you have to do modes this way. I'll point out a couple of things I like about this. On most of our missions, we try to keep the number of modes down pretty low. This has 5, and I'll talk about it. You don't need 5. You could do 4, you could do 3. It totally depends on what your mission is trying to do. But each of our mission modes serve a function. And the important part of this diagram is that we've identified how they interrelate to one another. This is the kind of thing you want to start thinking about. You want to involve your software team. They should not be a part of this process because this impacts them the most. Modes also give you a framework, again, like I said, to start talking about your budgets and things like that. And really, again, starts to help flush out what you're actually doing in a given state and then what you need to design to accommodate that. A couple of best mode definition best practices. So I don't think this is actually a formal requirement in UNP, but I could be wrong. You probably should have a safe mode. You can call it safe mode. You can call it something else. It totally depends on what you're trying to do, but you need a safe mode. And what I mean by a safe mode is you need a mode that you can send the satellite to that it can hang out in for an indefinite period of time. If and when something goes wrong during operations, you can say, okay, fine, put it into safe mode while we figure this out. And that doesn't mean that everything's off. That's not a safe mode, right? You're probably most safe when you're power positive and you're able to talk to the satellite. And beyond that, you could probably have everything go wrong, but you'll still be able to recover, right? Maybe it depends on the system, but that's the way you want to start thinking about this. So have a safe mode. Think about a recovery tree. So graceful mode, degradation and promotion is good. If we think about, and I'll flip back to it, but if you think about the diagram I showed you most recently, there was a degradation. I couldn't get from demonstration or experiment mode all the way into my worst case safe mode. I had to go through a couple of things so that the satellite could make some assessments and tell me, the operator, what's going on before it totally kicked into a rough state, right? Consider what mode the spacecraft comes up on post reset is a part of this as well. So if you have a power reset, whether fault triggered or something else, you want to make sure that you come back gracefully. And so all of these things are important to think through. I don't have a way to tell you exactly how to do that because it's going to depend on you and your hardware and your mission. Mode transitions, like I said and highlighted on the last diagram, this is important to be very thoughtful about. Be very clear about how modes get between one another. An example, you want to think through, what are you going to allow to be an automatic mode transition through either a fault or an auto promote? And what are you going to require an operator in the loop to command? I also make a note here that fault triggered mode transitions are sometimes very necessary, but be careful with them. You don't want to trip into safe mode for every little thing, right? So being thoughtful about that is probably the most important thing I can emphasize here. And when we start talking about software design and fault handling, this is just kind of the overall precursor. I think there's an EIT on that later on, which will give you far better insight. But as you're building your ConOps, these are kind of the pieces that you want to think about, even if you haven't fully fleshed out what fault handling looks like. We kind of covered the ConOps elements. Now we're going to jump into a culmination of all of those based on our experiment plan. So we'll just do experiment A. Remember, that's our mission success criteria for this program. I think it was called CARSAT, but regardless, for our example mission, we're trying to take one picture a day on a single location for 7 days. So experiment A, ConOps description, we're going to have our satellite in an operational mode. We're going to schedule the data collects for targets. The vehicle will then collect data, and then the vehicle will downlink that data. So this is a high level overview. This is what we're trying to do, right? That aligns with our experiment plan. We're then going to say our experiment objectives are to collect the images and then downlink the images. So we don't complete the experiment until our images are downlinked. That was a design decision. You could say your experiment's complete before that. I don't think many stakeholders would be fine with that, but maybe they would be. It totally depends on your mission set. The desired data product, and we're doing a single pass data collect with timestamp GPS correlated. Maybe that's necessary, maybe it's not, depends on what your requirements are or your objectives are. The missing thing here should be for 7 days, right? So you want a single pass each day for 7 days. We start to break this down even more of, okay, here's my explicit entrance criteria. Here's my explicit exit criteria. What are the ways I get into the experiment? What are the ways I could get out? And they are not necessarily serial. Maybe there's several ways you get in and several ways you get out, depending on how it goes, right? So an example, your experiment entry criteria is, okay, maybe all of these are required. So I say the vehicle is in a healthy state. I'm an operator. I can check that. The target is identified. Someone told me what they want to see, and the vehicle is in operations mode, and I commanded it that way. The experiment exit criteria could result poorly, right? So all experiment data is downlinked and the schedule is executed and complete. Cool, I did it correctly. I made my experiment. You can also exit experiment from a fault, right? And so that's something to think about related back to that mode transition diagram when you're starting to write out all these pieces. Operational mode state, this is a example of what I was talking about earlier. Each mode should have kind of a state definition for what your data resolution collect is, what data type you're getting. Maybe each system produces different data types, right? The example here is the payload. You've got telemetry and you've got mission data. This is something you want to define for each, however you break out your ConOp. Maybe it's on an experiment basis, maybe it's a mode basis, but you want to make sure you've kind of understood that, because that's important for your data budget. It's important for your power budget, and it's important for things like thermal as well. Similar to the experiment plan, now we're talking about what the ConOps document informs. So like the experiment plan, because there's a lot of overlap, again, you're going to inform your budgets, you're going to inform your requirements and component selection. Ultimately, it also drives your communications architecture, so your ground system requirements and overall trades. And so I guess the whole point of this slide is that this is an important document for you to start to bridge that gap between your objectives and your requirements and your budgets. And so this is a tool for you to utilize through that effort, and it will help you communicate and understand accordingly. In summary, we've talked about these two things and all their subcategories, ultimately all the ways that can help you. And really the statement here is these documents will be as useful to you as you make it, and they are living, right? So you don't have to do your ConOps and say, I'm done. It's FRR. I have a completed ConOps. No, these things will change with the life cycle of your program. And ultimately, you're going to try to execute both of these documents in mission ops, and they'll change then too. And that's okay. Again, the goal is not to have a perfect document, right? But it's to have appropriate communication of what we're doing here and how we're doing it. The last two slides I have are what I'm calling self-assessments, but really what I tried to map out, I'll flip back to this for you, is at what stages of the program do these help me and how? And so the way that you use the experiment plan now at SCR is going to be very different in how you use it at PDR, which is going to be very different than how you use it at operations. And so it's important to kind of do a self-check. And these questions are all encompassing. But the real question is this document useful to you? And if it's not, what information is it missing? So in example, now you guys are all somewhere between SCR and SRR. Are your objectives achievable? Does your experiment plan help inform that? Is the mission achievable on a small sat? And have you done enough in your design work in the experiment plan to tell you that? Ultimately, as a communication tool, do your stakeholders understand what you're trying to do? So think through, as you're starting to create this, some of those perspectives, I suppose. Similar with the ConOps. And one thing I'll note that I think either Dr. Lee Jasper or Dr. Lauren Hunt told you was you'll start to see the ConOps become more and more important, as shown here, and the experiment plan become less and less leaned on. And that's probably true. But you want to make sure that you're leveraging both, particularly in this early phase as you're starting to spin up your design. I think we're close to out of time, but that's all I have. Any questions?